Hello everyone, today we are going to analyze this beam using Kani's method. Before analyzing, let us see the beam one time. In this beam, there are three spans, span AB, span BC and span CD. In the span AB, there is a concentrated moment 25 kN meter acting at 2 meter from the point A. In the span BC, there is a concentrated moment 20 kN meter acting in the center. Both of the moments are acting in the clockwise direction. In the span CD, there is a concentrated load 12.5 kN acting at 3 meter from the point C. In the points A, B and C, there are hinged supports. In the point D, there is a fixed support. Span AB is 5 meter long. Span BC is 4 meter long. Span CD is 5 meter long. In this beam, totally we have to find 5 moments. In the point A, there will be no movement because it is the simply supported end. In the joint B, there are 2 moments, MBA and MBC. In the joint C also, there are 2 moments, MCB and MCD. In the point D, we are having a fixed support. In the fixed support, there will be a moment. Here the moment is MDC. So totally we have to find 5 moments. Also, we have to find 4 vertical reactions RA, RB, RC and RD. Now we are going to find the fixed end moments. First, let us take the span AB and find the fixed end moments. In the span AB, there is a clockwise concentrated moment. This moment is not acting on the center. The formulas to calculate the fixed end moments are minus mb upon L square into B minus 2a and ma upon L square into 2b minus a. Here m is 25, a is 2, b is 3. When we apply the values inside the formulas, we are getting m of ab and m of ba. Now let us make the fixed end moments in the span BC. In the span BC, there is a clockwise concentrated moment. This moment is acting in the center. The formula for the fixed end moments are m upon 4 and m upon 4. After applying the value of m in the formula, we are getting m of BC and m of CB. Now let us make the fixed end moments in the span CD. In the span CD, there is a concentrated load 12.5 kN. It is not acting on the center. The formulas to calculate the fixed end moments are minus WAB square upon L square and positive WA square B upon L square. Here W is 12.5, A is 3, B is 2, L is 5. When we apply the values inside the formulas, we are getting M of CD and M of DC. We know that in the point A, there will be no movement because it is a simply supported end. So MAB is equal to 0. So we have to make AB 0. For AB, the fixed end moment is 3. When we add minus 3 with this 3, it will be 0. We have released AB and made it 0. Then we have to give carry over from AB to BA. the carryover should be done in the same way we did in the moment distribution method. When we divide minus 3 by 2, we will get minus 1.5. Now let us calculate the adjusted fixed end moments. For BA, we have to add these two values. After adding, we are getting 6.5. For BC, CB, CD and DC, there are no changes. In Kani's method, we have to find the rotation factor. To find the rotation factor, we have to calculate the stiffness. Let us see the formulas to calculate the stiffness. If the fair end is fixed, the formula is 4EI upon L. If the fair end is hinged or with roller support, the formula is 3EI upon L. If the fair end is continuous, the formula is 4EI upon L. First, let us calculate the stiffness for BA. For that, from the joint B, we have to look at the point A. In the point A, there is a hinged support. If the fair end is hinged, the formula is 3EI upon L. Length of BA is 5 meter. Let us apply that. Finally, we are getting 0.6 EI. Now, let us calculate the stiffness for BC. For that, from the joint B, we have to look at the point C. The point C is continuous because after the point C, there is a span CD. If the fair end is continuous, the formula for stiffness is 4EI upon L. Length of BC is 4 meter. Let us apply that. Finally, we are getting EI. Now, let us calculate the stiffness for CB. For that, from the joint C, we have to look at the point B. The point B is continuous because after the point B, there is a span BA. If the fair end is continuous, the formula for stiffness is 4EI upon L. Length of CB is 4 meter. Let us apply that. Finally, we are getting EI. Now, let us calculate the stiffness for CD. For that, from the joint C, we have to look at the point D. In the point D, there is a fixed support. If the fair end is fixed, the formula for stiffness is 4EI upon L. Length of CD is 5 meter. Let us apply that. Finally, we are getting 0.8 EI. Now, let us calculate sigma K. In the joint B, there are two stiffness values. Let us add both of them. After adding, we are getting 1.6 EI. In the joint C also, we have calculated two stiffness values. Let us add both of them. After adding, we are getting 1.8 EI. Now, let us calculate the rotation factor. The formula is minus 1 upon 2 into K upon sigma K. We have already calculated the values of K and sigma K. Using the formula, we can calculate the rotation factors. In Kani's method, we have to make boxes like these in the joints. In this beam, there are two joints, joint B and joint C. So in these joints, we are making these boxes. Then let us enter the fixed end moments. For AB, it is 0, so no need to enter. For BA, it is 6.5. For BC, it is 5. For CB, it is 5. For CD, it is minus 6. And finally, for DC, it is 9. Now, let us add the fixed end moments in the joints. In the joint B, there are two fixed end moments. Let us add them. After adding, we are getting 11.5. In the joint C also, there are two fixed end moments, 5 and minus 6. Let us add both of them. After adding, we are getting minus 1. Then let us enter the rotation factors. In the joint B and the joint C, we have calculated the rotation factors. Let us enter them. For BA, it is minus 0.1875. For BC, it is minus 0.3125. For CB, it is minus 0.2778. For CD, it is minus 0.2222. In Kani's method, we have to find the rotation contribution. We have to find the rotation contribution in the joints. Here there are two joints, joint B and joint C. In the joint B, there are two rotation contributions, M-BA and M-BC. In the joint C also, there are two rotation contributions, M-CB and M-CD. Let us see the formula to calculate the rotation contribution. Summation of rotation contributions at fair end plus summation of fixed end moments into rotation factor. Now let us calculate M-BA. M-BA is located in the joint B. For the joint B, the fair ends are the point A and the point C. In the point A, the rotation contribution is 0 because we have already released AB and made it 0. In the point C, initially the rotation contribution M-CB will be 0. So for the summation of rotation contributions at fair end, we have to add 0 and 0. The summation of fixed end moments is 11.5. The rotation factor for BA is minus 0.1875. Finally, we are getting M-BA is equal to minus 2.156. Now let us calculate M-BC. For M-BC, all the values in the formula will be same except the rotation factor. For BC, the rotation factor is minus 0.3125. Let us apply that. Finally, we are getting minus 3.594. Let us enter the value of M-BA here and M-BC here. Now let us calculate M-CB. M-CB is located in the joint C. For the joint C, the fair ends are the point B and the point D. In the point B, the rotation contribution is minus 3.594. In the point D, the rotation contribution is 0 because in the fixed support there will be no rotation contribution. For the summation of rotation contributions at fair end, we have to add these two values. The summation of fixed end moments is minus 1. The rotation factor for CB is minus 0.2778. Finally, for M-CB, we are getting 1.276. Now, let us calculate M-CD. In the formula for M-CD, all of the values will be same except the rotation factor. The rotation factor for CD is minus 0.2222. Finally, for M-CD, we are getting 1.021. Let us enter the value of M-CB here and M-CD here. We have finished the first cycle. Now let us start the second cycle. In the second cycle, let us calculate M-BA. The rotation contribution in the point A is 0. Now in the point C, we are having the rotation contributions. We have to select M-CB, which is 1.276. So for the summation of rotation contributions at fair end, we have to add 0 and 1.276. The summation of fixed end moments is 11.5. The rotation factor for BA is minus 0.1875. Finally, for M-BA, we are getting minus 2.395. Now, let us calculate M-BC. The rotation factor for BC is minus 0.3125. After calculations, we are getting minus 3.992. Let us enter the value of m dash BA here and m dash BC here. Now let us calculate m dash CB. The latest contribution in the point B is minus 3.992. The contribution in the point D is 0. The summation of fixed end moments is minus 1. The rotation factor for CB is minus 0.2778. Finally, for M-CB, we are getting 1.387. Finally, for M-CB, we are getting 1.387. Now, let us calculate M-CD. The rotation factor for CD is minus 0.2222. After the calculations, we are getting 1.109. Let us enter both of the values. We have finished the second cycle. Now let us start the third cycle. In the third cycle, let us calculate m-BA. The rotation contribution in the point A is 0. The latest rotation contribution in the point C is 1.387. So the summation of rotation contributions at fair end is 0 plus 1.387. The summation of fixed end moment is 11.5. The rotation factor for BA is minus 0.1875. After the calculations, we are getting m-BA. Now let us calculate m-BC. The rotation factor for BC is minus 0.3125. After the calculations, we are getting m-BC is equal to minus 4.027. Let us apply the values of m-BA and m-BC. Now let us calculate m-CB. The latest contribution in the point B is minus 4.027. The contribution in the point D is 0. So for the summation of rotation contributions at fair end, we have to add these two values. The summation of fixed end moments is minus 1. The rotation factor for CB is minus 0.2778. After the calculation, we are getting m-CB is equal to 1.396. Now let us calculate m-CD. For that, we have to apply the rotation factor for CD. Finally, for m-CD, we are getting 1.117. Let us apply the values of m-CB and m-CD here. We have finished the third cycle. Now let us make the fourth cycle. The fourth cycle should be made in the same way we did for the previous cycles. You can see the calculations. You can see that in the third and in the fourth cycles, all of the values are approximately same. So we can stop in the fourth cycle. Now let us calculate the final moments. The formula is fixed end moment plus 2 into rotation contribution at near end plus rotation contribution at fair end. Let us make one table. In the table, first let us enter all of the numbers. Then let us enter the fixed end moments. Then let us enter 2 into near end contribution and fair end contribution. We have to be very careful. For AB, we should not add 2 into near end contribution and fair end contribution because we have already released AB and made it 0. For BA, the near end contribution is minus 2.418. So 2 into minus 2.418. For BA, the fair end is AB. In AB, the rotation contribution is 0. For BC, the near end contribution is minus 4.03. So 2 into minus 4.03. For BC, the fair end is CB. In CB, the contribution is 1.397. For CB, the near end contribution is 1.397. So 2 into 1.397. For CB, the fair end is BC. In BC, the contribution is minus 4.03. For CD, the near end contribution is 1.118. So 2 into 1.118. For CD, the fair end is DC. In DC, the contribution is 0. Now let us take DC. For DC, the near end contribution is 0. For DC, the fair end is CD. In CD, the contribution is 1.118. Now let us add these three values and get the final moments. After adding, we are getting the final moments. In this analysis, we have calculated all of the moments. Now we are going to find the vertical reactions. First, let us take the span AB and calculate the vertical reactions. In the span AB, there is only one moment, that is MBA, which is acting in the clockwise direction. In this span, first I am going to calculate RA. For that, I am going to take moment about B. In this case, I am moving towards right hand side. Clockwise will be positive and anticlockwise will be negative. RA is acting towards the point B in the clockwise direction, so it will be positive, and the distance is 5 meter, so 5 RA. Then there are two moments, 25 and 1.66. Both of them are acting in the clockwise direction, so both of them are positive. Finally, for RA, we are getting 5.33. For RA, we got a negative value. That means our assumption is wrong. We assumed that RA is acting upwards, but actually it is acting downwards. Now let us apply the rule summation of vertical forces is equal to 0 and calculate RB1. In this span, there are two vertical forces, RA and RB1. We know that RA is acting downwards, so it should be negative. RB1 is acting upwards, so it should be positive. Here, let us apply the value of RA. In this way, we can calculate RB1, which is equal to 5.33 kN. Now let us take the span BC and calculate the reactions. In the span BC, there are two moments, MBC, which is acting in the clockwise direction, and MCB, which is acting in the anti-clockwise direction. In this span, first I am going to calculate RB2. For that, I am going to take moment about C. RB2 is acting towards the point C in the clockwise direction, so it will be positive and the distance is 4 meter. So 4 RB2. Then there are three moments. 1.66 moment is acting in the anti-clockwise direction, so it will be negative. The moments 20 and 3.76 are acting in the clockwise direction, so both of them are positive. Finally, we are getting RB2 5.53 kN. For RB2, we got a negative value. That means our assumption is wrong. We assumed that RB2 is acting upwards, but actually it is acting downwards. Now, using the rule summation of vertical forces is equal to 0, we can calculate RC1. After applying the rule, we are getting RC1, which is equal to 5.53 kN. Now let us take the span CD and calculate the vertical reactions. In the span CD, there are two moments, MCD, which is acting in the anticlockwise direction, and MDC, which is acting in the clockwise direction. By taking moment about D, we can calculate RC2, which is equal to 3.73 kilonewton. By applying this rule, we can calculate RD, which is equal to 8.77 kilonewton. In the point B, we have calculated the reaction 2 times. Let us add both of them. After adding, we are getting 0.2 kilonewton. For RB, we got a negative value. That means it is acting downwards. For RC also, we have calculated the reaction 2 times. Let us add the values. After adding, for RC, we are getting 9.26 kilonewton. Now, we are going to draw the shear force diagram. Before drawing the diagram, let us calculate the shear force values. I am going to calculate the shear force values from the point A and towards the point D. In this case, I am moving towards right hand side. Upwards will be positive and downwards will be negative. You can see the shear force calculations using the values. We can make the shear force diagram. Now we are going to draw the free movement diagram. For drawing the free movement diagram, we have to consider every span as a separate simply supported beam and calculate the moments. If in the simply supported beam, concentrated movement is acting in the clockwise direction and it is not acting on the center, the formula to calculate the ordinates are mb upon L and ma upon L. Here m is 25, a is 2, b is 3. After applying the values inside the formulas, we are getting 15 and 10. On the left side of the movement, it will be negative, and on the right side, it will be positive. If in the simply supported beam, concentrated movement is acting in the clockwise direction, and it is acting on the center, the formula to calculate the ordinates are m upon 2 and m upon 2. Both of the formulas are same. Here m is 20. After applying the values inside the formulas, we are getting the ordinates 10 and 10. On the left side of the movement, it will be negative, and on the right side, it will be positive. Then let us take the span CD. Here there is a point load 12.5 kilonewton. It is not acting on the center. The formula to calculate the ordinate is WAB upon L. Using the formula, we are getting the ordinate 15. Now, using the end moments, we can make the end moment diagram. Then we have to combine the free moment diagram and end moment diagram. So we will get the bending moment diagram. Now we are going to end this session. Thank you for watching this video.